All right, let's go way back to the very beginning of artificial intelligence, to talk about one of the first, most fundamental algorithms ever created, the perceptron. This is the story of a super simple idea that honestly kicked off a revolution. It all starts with a question that seems almost childishly simple. How do you teach a machine to tell two things apart? Like sorting apples from oranges or figuring out if an email is spam or something you actually want to read. This basic act of sorting is called classification, and it's the bedrock of so much of what AI does today. And believe it or not, this is not a new question. While AI feels like it's exploding right now, people have been wrestling with this idea since the dawn of computers. I mean, look at this paper. This is from 1962. They were already diving deep into the math behind these early learning machines. The roots go way, way back. So if we really want to understand how we got to today's incredible AI, we have to start at the beginning, with the invention of a machine that could actually learn. Our story really kicks off in 1943 with this wild idea. What if we could model a brain cell, a neuron, just using math? Fast forward 15 years to 1958, and a psychologist named Frank Rosenblatt takes that idea and runs with it, creating a learning algorithm he calls the perceptron. And then, a few years later in 62, the math finally caught up, proving that his invention was the real deal.
So what on earth is a perceptron?
Well, probably the easiest way to think about it is as a single, really simplified digital brain cell. At its heart, a perceptron is just a decision maker. It takes in some information, chews on it for a second, and spits out a simple yes or no. Is this a picture of a cat? Yes or no? Is this a fraudulent transaction? Yes or no? It's the absolute most basic building block of what we now call neural networks. And how it makes that decision is actually pretty straightforward. It looks at different pieces of evidence, which we call inputs. For each input, it decides how important it is. That's the weight. Then it just adds everything up. A final rule, the activation function, makes the call. If the total score is high enough, it shouts yes, +1. If not, it says no, -1. And this simple idea of learning the right weights for things, that is the absolute core of how even the most powerful modern AI works. But here's the million-dollar question. How does it figure out what the right weights are? How does it actually learn? Well, this is the most elegant and honestly beautiful part of the whole thing. It learns by messing up. The process is just so intuitive. The perceptron makes a guess. If it gets it right, it does nothing. It just says, okay, cool, and the weights stay exactly as they are. But if it gets it wrong, it slightly adjusts those weights to learn from that specific mistake. It just does this over and over, one example at a time, getting a tiny bit smarter with every single error. If you try to picture this, the perceptron's whole goal is just to draw a single straight line that cleanly separates two groups of data. Now, if you have more than two features, that line becomes a flat plane, or what mathematicians call a hyperplane, but the idea is exactly the same. Okay, let's actually watch this happen. Imagine the pluses are one category and the minuses are another. That solid line is the perceptron's current best guess at how to separate them. This visual says it all. See how the first line gets it wrong? It puts one of the pluses on the wrong side. So the algorithm sees this mistake, it adjusts its weights, and boom, the new dashed line has tilted just enough to fix that one error. It's learning, one mistake at a time. Now, this process of just nudging the line around seems like it should work, but it raises a really, really important question. I mean, is it actually guaranteed to find the solution? Or is it possible that by fixing one mistake, it just creates a new one somewhere else, and the line just wiggles back and forth forever, never settling down? This was the critical question for those early AI pioneers. And the answer, which was a massive, massive breakthrough, is a hard no. The perceptron convergence theorem is this powerful guarantee that says if a solution exists, meaning if you can separate the data with a straight line, the perceptron algorithm is guaranteed to find it. And it won't take forever. It'll find it in a finite number of steps. It's even cooler than that. The theorem actually gives us a mathematical formula that puts an upper limit on the number of mistakes the algorithm will ever make. This formula basically says the number of errors is capped depending on things like how spread out your data is. So this wasn't just a hopeful hunch, it was a mathematical certainty. And when you look at these original papers, you can just feel the excitement. This guarantee gave the whole field a huge shot of confidence. They had built a machine that was mathematically proven to learn, at least for certain types of problems. And that brings us to the twist, because researchers soon discovered the perceptron's kryptonite, A simple little logic puzzle that this brilliant algorithm was completely powerless against. It was called the XOR problem. XOR stands for exclusive OR. The rule is simple. The answer is true if one thing or the other is true, but not if both are. Now, if you plot these four possibilities on a graph, you get 2 points in one class and 2 in another. And here's the punchline. Try it. You literally cannot draw a single straight line that will cleanly separate the two groups. It is mathematically impossible. No matter how many times the perceptron tries to update its weights, it will fail forever. This is what we call a non-linearly separable problem, and the discovery of this simple limitation sent a shockwave through the AI community. It exposed the hard limits of these early models and was a major factor in what's now called the first AI winter, a time when funding and interest in the field dried up. But that's not where the story ends. In fact, the perceptron's biggest failure became the inspiration for its greatest successor. Researchers had an epiphany. Okay, one line can't solve the problem, but what if we used multiple lines? By stacking layers of these digital neurons, creating what's called a multi-layer perceptron, they could create complex, curvy decision boundaries. Of course, this new setup needed a whole new way to learn, and that led to the invention of backpropagation, the engine that drives nearly all of modern deep learning today. So in the end, the story of the perceptron is the perfect story of science. You have a brilliant idea, a powerful guarantee, a crushing limitation, and then a whole new wave of innovation born from that failure. It just leaves you with this incredible thought. If one single, simple digital neuron could start this entire journey, what are the limits when we start wiring billions of them together?